Welcome to our webinar, Ejecta from Dimorphos. I'm Julie Hong, a sophomore from Wellesley High School and a student volunteer for the Planet+AI program. I'll be your moderator for today. Our speaker today is Dr. Jian-Yang Li, a senior scientist at the Planetary Science Institute. Dr. Li will give us a presentation on his team's observations of NASA's Double Asteroid Redirection Test mission's Ejecta from Dimorphos. Dr. Li is a DART investigation team member and the lead of the Hubble Space Telescope observations of the impact ejecta. This event is sponsored by the TN Space Grant Consortium at the University of Tennessee, Knoxville. And this event will be recorded and will be available online after the end of our webinar. Please mute yourselves before our presentation. If you have any questions, feel free to enter them into the chat at any time. Our speaker will answer your questions as time permits. Dr. Li, we are looking forward to the presentation, so over to you.
All right, thank you. Thank you, Julie. I'm very glad to give the talk today, and I heard that you will all follow up with AI arts based on the ejecta from Dimorphos, based on DART mission, maybe based on planetary defense. So I'm very excited about this, and I will do my best to help your art creation. And I will give you some background about the DART mission, about planetary defense, and I will also then show you a lot of beautiful images we take for the ejecta from DART. All right, now let's see. Okay, so this is a one-slide summary of DART mission. As many of you have probably known, DART was launched in November 2021. And after about 10 months cruise, it approached its target and made a successful impact on Dimorphos, which is the moon of a double asteroid, double asteroid Didymos. As shown in this image, this figure, the primary asteroid of this system is called Didymos, and we are hitting the secondary small number of this system. And the diameter of this of the target is 150 meters. And also coming with DART, there's a small CubeSat. It's called LiCiCube. That's contributed by Italian Space Agency, and that LiCiCube piggyback with DART spacecraft, and it was released about 2 weeks before the impact, and then it slowed down a little bit, divert its trajectory a little bit, then fly by from the system to look at the ejecta from very close distance. And in the meantime, there are a lot of telescopes on the Earth and also in the near Earth space that are looking at the system, looking at the impact of the ejecta. So that is the basic, one slide summary of the DART mission. Now, the question is, why are we doing DART? You know that DART is a planetary defense mission, so it has a planetary defense background. Why are we defending our Earth? This figure shows the fireballs reported by the U.S. government sensors on the globe. You can see that there are so many fireballs happen on the Earth, and there are many space debris or small rocks or large rocks, small asteroids that hit Earth every day, almost every day. But many of them are tiny, so they just make some meteors. But some of them are quite big that can, cause some real damage to us. And this big red dot, that's the Chelyabinsk impact, and that happened in 2011. So I guess many of you probably have known that this impact caused caused an air burst, and then that injured thousands of people in Chelyabinsk, Russia. And all of you must have known that 65 million years ago, dinosaur extincted, and right now people just the most commonly accepted theory is that there was a 10-kilometer diameter asteroid hitting the Earth, and then that caused a global disaster and caused the mass extinction on Earth. So certainly we don't want that to happen again. And so that is there's a need for planetary defense. We need to defend us from this kind of impact disaster from space. So planetary defense is actually oh yeah, that's Chelyabinsk. It's actually a big topic, and it has several components. We go from top right, we need to search, we need to detect, and we need to track these potential impactors to Earth. And then once we observe them, we need to characterize it, how big they are, how dense it is, and what trajectory it has. So all this kind of characterization, we need to know its properties in order to best defend us. Then we need to plan and coordinate. So there are some government agency here, some international agency that are responsible for planning, for coordinate how we're gonna mitigate the impact disaster. And then here comes the mitigate. Mitigate is coordinated by several government branches, and also there's a office, the Outer Space Affair Office in the UN also is responsible for these kind of affairs. And then FEMA in the US, that's responsible for this for the mitigation, for coordinate the mitigation. Then DART fits into this part. We're basically testing our technology to mitigate asteroid impact to Earth. The way is that we kind of divert the asteroid a little bit so it does not hit Earth. Of course, there are some other components, some other ways to mitigate. And then finally, after that, we need to assess. We need to know, assess how well we did it, and whether we did it well enough, and what lessons we learned. So that's the whole planetary defense, whole picture of planetary defense, and the art fits into the mitigation. Now, speaking of mitigation, they are, I'm showing a graph that has the x-axis is the warning time, meaning that, okay, now we discover an asteroid, and we know that it's going to hit Earth in how many years. So that's a warning time, how much time we have before the impact. And then the y-axis is the diameter of the asteroid, so how big it is. And depending on these two parameters, we will need to use different strategies. So basically, what this figure shows is that we depending on these two parameters, what technique we should use. And if we have enough leading time, and if the asteroids are not too big, falling in this green, yellow shaded region, then we should be able to deflect it. So with time, the small difference with small push we make on the asteroid will accumulate, and then it will eventually miss Earth. Then if it's big, then we will need to use some more powerful ways, like nuclear deflection or even nuclear disruption, if the warning time is too short. Now, if warning time is really short, only a few years, basically we have nothing. We have no way to do anything. And then if the asteroids are really small, like smaller than 50 meters or 30 meters, it will not actually hit the Earth. It's gonna burn up, it's gonna explode in the air in very high altitude. So we don't have to do anything either. And DART, that actually fits into the kinetic impact deflection category. This part, we're basically testing a technology that is going to be able to deflect an asteroid maybe 100, 200, a few hundred meters across, and when we have enough warning time, like 10, 20 years or more. And this kinetic impact deflection technique is actually the most mature technique that we can test. So that's why we're doing this test now. But now, another question is, you will probably ask, okay, we know that we're gonna impact, if we send a spacecraft or some whatever to impact an asteroid, we're going to push it. And the target will be with the spacecraft carries some momentum, and then that momentum will be transferred to the target, right? So what do we need to test? Why do we need to test? The thing is that it's not like that. Not like that. It's not simple. Okay, so because any impact onto an asteroid will cause a lot of ejecta. Um, if there's no ejecta, so basically the momentum we transfer to the target will be the momentum that's carried in by the spacecraft. But if we generate some ejecta from the target, then the ejecta will come out towards the spacecraft, the direction the spacecraft coming, right? So the ejecta will carry out some momentum, and that's going to actually enhance the momentum transferred to the target. So the more ejecta you have, the higher the faster the ejecta you can excavate in the impact, the more momentum enhancement we will have. So the more effective this push will be. But we actually know very little about this impact, the cratering process on asteroids. So we really have no way to make good predictions. Before the impact, our team actually did a lot of observations to determine the target properties, and then run numerical simulations to calculate, to estimate how much push we can get. And we do have a range of estimate for the enhancement factor, which is from 1 to 5, a huge range. So basically, that means we have no way to predict the outcome. So that's why we want to do the test. We want to know more about the impact process onto an asteroid, and we want to make better predictions for in the future when we have to do this. Okay, now the target. Why are we hitting a double asteroid? And why, in particular, why are we hitting the moon of a double asteroid? Why don't we just hit any asteroid? This is actually a very smart part of this mission, of the idea. The reason is because, with the impact, we can only push the asteroid, change the speed of the asteroid this much, actually very little. In particular, DART changed the speed of the target by about 3 millimeters per second. Very small, right? So if we hit an asteroid that is orbiting the sun, the orbital speed of that asteroid will be something like 30 kilometers per second. So we only give it a very, very tiny push. And that push will change the orbit of the asteroid around the sun by only a few seconds. Now imagine, how can we measure that a few seconds change out of like 1 year or 2 year orbital period? It's basically impossible. But if we hit the moon of a double asteroid, then we will be able to change the period of the moon around the double asteroid a lot. This is because the orbital period of this moon is only like 20 centimeters, 0.2 meters per second, compared to the heliocentric velocity of 30 kilometers per second. So this actually caused, with this small push, we will be able to change the orbital period of the moon, in particular the Dimorphos around Didymos, by half an hour. This is what we actually did. And the orbital period of Dimorphos before impact was around 12 hours. So with this big change, it's actually much easier to measure. So that's one reason, we want to hit the moon of a double asteroid. That's because it's much easier. That makes us to be able to measure the outcome of the impact. Right. There's another reason that we are hitting this particular target. The other reason is related to the measurement, how we can measure the orbital period change of this double asteroid system. That is because for this particular target, at some particular time when the Earth and the asteroid and the sun, the mutual geometry of the three objects are at the right position, these two asteroids, the Earth is close to the orbital plane of the moon of this double asteroid. So when the moon is orbiting Didymos, the two objects will block each other. So that means, that is called occultation. Okay, let me communicate. And also, they will go to the shadow of one another. That's called eclipse, right? So once that happens, the total brightness of this asteroid system will have a dip. That's shown on the bottom. basically from the Earth, there's no way we can resolve these two objects. They are too small. They're too tight, and they're too far from the Earth. But by looking at the total brightness and the dip caused by the mutual blocking, we call that mutual event, we can precisely measure the period of this system, right? And then after the impact, the phase where the moon is around the Didymos will change a little bit. And this is 1 day after the test. The light curve is shown by the orange line. There's only a slight difference, slight offset, right, between the post-impact light curve and the pre-impact light curve. But the good thing is that this small offset actually accumulates with time. Now, after a few weeks, several weeks, you can see that the phase of these two light curves are completely off. So basically from this, we can very precisely measure the post-impact period. And on the right, these are the two periods are the pre-impact periods and post-impact periods. So, this design then makes the mission design very simple. We just send one spacecraft and then hit it. And then everything else, we can do it from the Earth, right? So that's the reason that we're hitting the moon of a double asteroid, and the reason that we're doing this particular target. So very simple design of the spacecraft. We just need a spacecraft, right? Basically, to hit it. And then another essential component is the camera. It's called Draco. It's called Didymos Reconnaissance and Asteroid Camera for optical navigation, right? So this is just a navigation camera. And this is the only science payload on board this spacecraft. It has a pair of huge solar panel and also some other components, but most of those are just for technology demonstration. Basically, NASA wants to make the most out of the mission, so they packaged a lot of new technology on it. Essential, non-essential components, not essential for this particular mission, but they can test the new technology. And also there's a literature cube, as I mentioned. It's contributed by Italian Space Agency. That's going to look at the impact from close distance, right? So this is the Italian CubeSat, very small size. And it carries two cameras, Leia and the Luke. Leia is a long-range camera, very high resolution camera, and only black and white camera. The Luke is a color camera, RGB color, but it has a lower resolution, a larger field of view. Okay, so this is the background of DART mission. Why we're doing that and how we're doing that. Now let's see what we actually did and what we actually get from the mission. So I don't know how many of you have was on the live stream before the impact. Draco camera takes 1 image per second, and then it streamed the images in real time back to Earth, and then NASA put these images online, and basically streaming the images in real time. So for people watching NASA TV, watching this broadcast in the same time, it was very exciting. Basically, you can imagine that it's like, let me play it again. It's like you're riding a spacecraft, approaching the target and hit it in very high speed. You can see that there are two asteroids here. This is Didymos, and then the real target is the moon, Dimorphos. And we're getting closer and closer. And we were watching this, and we were very excited. Everybody was like looking at this and see we're getting closer, and the target is becoming bigger and bigger. And then the last 5 seconds, we can see that this is the point that we are going to hit. And then once we see this final image, this is actually a partial image. Only a small fraction of this image was transmitted back before the spacecraft hit the target and destroyed. Right? When we see this image, this partial image, we were very happy. This is the first time we were happy about a bad image, right? So this is the last frame that has both Didymos and Dimorphos in the same frame. And this is of course the first time that any space mission has any space mission has seen a double asteroid. So this particular image is taken 2.5 minutes before the impact. And then this is a composite image of Dimorphos, the final target. You can see that towards the middle, the resolution is getting higher and higher, right? Because this is a composite, and we put together the final few images to enhance the resolution of the center part. So you can see it has a lot of rocks on the surface. This is just like any asteroid that we have seen, any asteroid of similar size that we have seen before. And as I mentioned, this is the impact site. The impact site is like in between three big boulders. And I don't have a scale bar here. The next slide, you will see a scale bar. And the impact site is right between in the middle of these three boulders. This impact site is not deliberately chosen. We just hit where we hit. So, and then after that, we know where we hit. So this is the final image with the spacecraft, marked on it. You can see that there are two large solar panels, and then the small square is the spacecraft bus. The total length is about, I don't remember, like 20 meters. And the size of these boulders, we now have names of these two big boulders. One is called Atabaki. The second is called Bodran. Their size are about 6 meters across. So that's basically the site that we hit. And then this is animation, made to show the spacecraft, how the spacecraft slammed into the area. The yellow thing is the model for the local topography, and then that's the spacecraft model, of course. You can see that looks like this solar panel hits the rock first. Then after maybe 1,000 seconds, the spacecraft bus, the main thing, hit the surface. So this, we are looking at a very detailed process because this actually matters for how we understand the cratering process, the ejecta excavation process. All right. Now, finally, after 20 minutes, now we get to the topic of this presentation, which is about the ejecta. Let's see what we made, what we did to Dimorphos. So this is a long-range camera, images from the long-range camera from LiCheCube, the flyby spacecraft, right? And this was taken, this short sequence was taken half minute before impact to half minute after impact. The timestamp is on the top. And this is these images were taken by Leia, which is the long-range camera. The Luke camera has the resolution of Luke was too low to see anything at this distance. But unfortunately, this camera was not focused. You can see that's why you see the donut shape, the ring of Dimorphos, not a circle. Then 1 second after impact, you see very bright ejecta. Then the brightness decreased, and then we see the big, a little fainter but much bigger ejecta coming out. So this is the only image that capture the moment right after the impact. Now, if we look at later images, these images were taken by LiCheCube as LiCheCube fly past the target from the side. I need to explain the geometry of these images, otherwise you won't be able to know what you're looking at. So let's wait until I look back. Okay, here. LiCheCube basically comes from where DART spacecraft comes in. So in this angle, the eject cone, we are basically fly towards the ejecta cone. In other words, the ejecta, is towards the line of sight, towards the LiCheCube. So we are looking into the ejecta cone. This is what these images are, right? And then after a while, after the closest encounter, we actually we fly by from the side. So now the whole ejecta cone flipped, and we're looking at it from the side. That's when you can see the nice cone shape of the ejecta, right? Now let's look at some more beautiful images from Luke. This is a long exposure image, where the bright blob is Didymos, and then there's another bright blob here that's Dimorphos, saturated, and also the base of the ejecta. And because this is a long exposure, you can see a lot of faint structure right here from the ejecta. A lot of ejecta rays or filaments that comes out. Very beautiful, very very complicated structures. You see a lot of some blobs here. And this image is a composite of a few images taken at different ranges. So basically, we are trying to put them together in order to see the features at different distances with different brightness. And we call this space spider. It looks like a spider, right? The saturated Didymos and Dimorphos and ejecta cone. And then there are the ejecta rays coming out from the center. And then there's all the features in it. And on the left, I put an image of deep impact ejecta just for comparison. You can see that they're so different. Deep impact impacted a comet, so comet Tempel 1, and you can see that ejecta is kind of smooth, very smooth ejecta ray coming from the center. But in case of Dimorphos ejecta, it has a lot of structures in it, quite different, and that's just because of the different target properties. Other than those features, this is another composite. In this composite, you can see there are also a lot of spots here, and these are actually boulders with size about a few meters. So these are big boulders compared to the structures you see that in other places in arrays. In array, those are composed of like millimeter or even smaller micrometer dust. But these are big boulders, a lot of big boulders entrained in the ejecta. And we're still trying to understand this, what we see here, why there are so many big ejecta, boulders there, and what they tell us. Okay, now let's back up, back to Earth and see what Earth-based space telescopes observed for the ejecta. So this sequence is taken about I would say half an hour within half an hour following the impact. And this is from LCGOT, that's in South Africa. This particular telescope. LCGOT is a telescope network, but these images was taken by the telescope located in South Africa. And you can see after impact, the brightness of Didymos or Dimorphos increase very quickly. And then there's a shell-like ejecta, like a poof, fast plume coming towards where DART spacecraft comes from. In this particular frame, DART comes from the right. Okay, and this is a very fast plume. It has the speed is about 1.5 kilometers per second, which is about 1 mile per second. Pretty fast plume, like shell shaped. And on the left, these are the two still images at two different times, 12 minutes and 15 minutes after impact. So these are the fast component of the ejecta. And after that, there are actually a lot of slow ejecta, which is what we saw in LiCheCube images that I just showed. These are the slower ejecta observed by James Webb Space Telescope. In near Earth space, both JWST and Hubble Space Telescope are looking at the ejecta. And this is actually the first time that JWST and the Hubble Space Telescope, the two generations of NASA great observatories, look at the same target at the same time. So first time collaboration for those two telescopes. So this one is these images are from JWST, taken within 5 hours after impact. What you see is that there are a lot of ejecta coming out. Some features just blow out from Didymos. And in this image, DART comes from lower left direction, about 45 degrees from horizontal, below horizontal. And then Hubble Space Telescope has observed the ejecta with much longer timeline. The observations start from about 1 hour before the impact until 18.5 days after impact. So that gives us a picture of how the ejecta evolved over about 3 weeks time period. So let me walk you through this image sequence. This one is pre-impact image. Basically, there's no ejecta. And what you see here, the diffuse thing, those are just the optical effect. The scatter light from a point source. And these spikes are, these lines are just the spikes. We had some pointing problem with Hubble Space Telescope. So that put the target very close to the edge of the camera. So that's why you see the edge here. Then this is like 0.4 hours, 20 minutes after impact. That's where we started to see the ejecta, diffuse and everywhere. And then next one, you started to see some structures there, and basically you see the cone. From this angle, we actually looked at the ejecta from the side. So what you see here is that there's a cone shape thing towards the left. Then, if I just go through the sequence, you can see similar to what JWST saw, but with sharper images, I would say. You can see this feature goes out, and then this all within the ejecta cone towards the left, right? Dart comes in from the left about, I would say 20, 30 degrees above the horizontal direction. And in the meantime, you can see that there's a long feature towards the right, extending towards the right and growing, right? That is the tail. That's because all these dust are pushed by solar light very gently, but strong enough, to push this dust out of the system. And that forms a tail. And this is very similar to the tails of comets. And this is actually the first time we see the growth of tail from impact ejecta. We have seen this kind of tail from asteroids a few times before, but we always miss the impact, of course. And this time we know when the impact happened, so we actually looked at it. We learned how the tail grows. Okay, and from this frame, you can see something very interesting happens. If you look at the center part, if I look back and forth a few times, the center part looks like there's a pinwheel, right? Some kind of spiral or pinwheel feature is rotating, right? And that feature is also unique. That only happens in a binary system. This is because we are hitting Dimorphos, which is orbiting Didymos, right? And so everything comes out from Dimorphos will be in orbit around Didymos. And if the ejecta are not very fast, if they're kind of slow, then we're gonna see the orbital motion of those dust, and that process created this kind of spiral shape. So if I flip back and forth a few times, you can see, feels like these features are rotating right around Didymos. So that's very interesting feature that we did not expect before the impact. Very surprised, very interesting. And if we move on, this is about 4.7 days after, what you see here is that all these features are shifted, are pushed towards the tail direction, right? Everything was pushed towards the tail. And this is also due to solar radiation pressure. Everything comes out, they are pushed by sunlight towards the tail direction. And this motion is coupled with their original speed, direction of the speed, which is not necessarily along the radial direction, right? So you can see a little bit rotate, then everything was pushed towards the tail. And in this process, you can see that there are some linear features, some lines formed here. So these are just because the dusts are not uniformly distributed in the ejecta. So they are elongated by solar radiation pressure and form this kind of a feature. And then this frame, these few frames are very interesting because there are two tails. We don't know why there are two tails yet. We're still trying to understand. We have a few hypotheses to explain it. but it's just we're still in a very early stage to say why there are two tails formed. And then by the final frame, basically all the ejecta around Didymos, around Dimorphos are dissipated. Most of them are pushed by solar radiation pressure towards the tail. So that's the end of Hubble observations. Oh, and I'm gonna skip this because I was trying to explain what we see, but we already seen those. I already explained those features. So this is a sequence connecting together the whole sequence of Hubble images, as I just described. Just I'll let it run until the end. So from these images, we get an idea how all these ejecta will come out from Dimorphos and how they interact with the binary system, and then they were pushed by the solar radiation pressure towards the tail. We learned the whole sequence of the ejecta evolution from these images. Similarly, another telescope on the ground, this is the VLT, Very Large Telescope of European Southern Observatory located in Chile. And it also took the image sequence as I just described from Hubble. So what you see here is also a sequence, and the ground-based telescopes has lower resolution than Hubble Space Telescope because we have atmosphere above us. But you can see similar structures. In the beginning, there's a ejecta cone coming out, then in the rotating feature, and then everything pushed towards the tail. Right? So these are the same sequence, just frame by frame. Now, from other ground-based telescopes, this is another very beautiful image from the ground. It's taken by SOAR, SOAR telescope located in Chile. This is a 4-meter telescope. And this is a composite image from different, I think three different filters. And that's why you see the red, green, blue color in the background. These are just the background stars. And the center, you can see that there's an ejecta cone towards the left, and then there's a long tail towards the right. This sequence is taken also on the ground from New Zealand. There's a telescope. I think this is a 2-meter telescope. And it covers from 1 day to 25 days after impact. Similar to what I described before, you have a ejecta cone, and then everything moves towards the tail, and then the ejecta clears out, and all the dust are in the tail. But this one is, of course, at a much lower resolution than the Hubble Space Telescope. And we actually, kept observing the tail since the impact, since the tail formed until now. I mean, not until now, but through now, and then we're still taking data. So I just want to show you what the tail changes with time. And this sequence was taken on mid-November by Lowell Discovery Telescope. This is a 4-meter telescope. What you see here is that, of course, there's no ejecta. The head is just the double asteroid, and then there's a long tail here, very narrow, straight long tail. I think the length is about is a few tens thousand kilometers, maybe 70,000-80,000 kilometers. So with time, the tail actually faded slowly. This image was taken at on November 30th, 2-meter telescope in New Mexico. And then the next one is a still image from the same telescope. And again, very narrow, long tail. You can see that the brightness of the tail is almost uniform in the beginning, and then decrease a little bit as you move further away from the asteroid. Now, this one is taken on December 25, the Christmas day last year. Now you can see that the tail is much fainter than before, right? Basically, the dust are dissipating with time. And also, in the meantime, Dimorphos is moving away from the Earth, moving away from the sun. So everything gets thinner. And now this one is taken in January 25. The direction of Didymos' movement in sky actually also changed. That also, that just depends on the mutual geometry between the Earth, the Earth and the asteroid. Now, really a thin tail. Again, February getting fainter, right? This is taken from Lowell 4-meter telescope. And these sequences were taken by Hubble from November 30th to March 1st this year. And you can see, if I just flip through, the direction of the tail changes, but that's just because of the mutual geometry between Earth, the asteroid, and the sun. So that's that we understand. But then the tail is getting, obviously getting thinner and thinner. By the last frame, it's barely seen here. And also you can see Didymos also is getting thinner because it's moving away from us and from the sun. Then this is the last image I want to show you. This is taken only a month ago from Lowell 4-meter telescope. And this particular stack, you can guess what's the total exposure time of this particular stack. I think if it's 5 hours of exposure time on the target. Only that you can see, a very faint tail. And all the background, those are background stars or galaxies, whatever in the sky that are smeared. So these are all the images and all the the stories about DART, about Ejecta from Dimorphos that I want to tell you. So I guess I can stop here, and I'm happy to answer any questions you have.
All right, thank you so much, Dr. Li, for your presentation. Let's see, we have some questions in the chat. How do we monitor near-Earth orbiter objects that may hit the Earth? How many are there? And is AI helpful in monitoring these objects?
Okay, well, we actually, near Earth objects, their orbits are close to the Earth orbit. So their orbital period is also, many of them are close to 1 year. That means they get close to Earth, then they leave, and then they remain far away from Earth for a long time. So basically, we don't have a way to monitor all of them. We just use telescopes to discover anything that we do not we don't know, and then we calculate their orbits, then we put it there, and then we basically put them in the database. We actually don't know many near Earth asteroids. I mean, okay, how many we know depends on the size, right? The larger they are, the brighter they are, and also the less we have. So we know more about the bigger asteroids, but for smaller asteroids, we actually don't know much. I think I actually have one more slide as a backup here. So the columns of this table, that tells us, that's just for asteroids of different sizes. For the bigger ones, on the right, for like 10 kilometer sized asteroids, there are only 4, and we know all of them in the near Earth space. And then for 1 kilometer objects, we know about 95% of them. But for smaller ones, like 140 meters, we only know less than half of them. And then for smaller ones, we basically don't know anything. We don't know them. So, we keep discovering where our focus is on the smaller objects, like hundreds of meters in size or smaller. And bigger ones, we don't have to know them. We don't have to worry about them because we know most of them, almost all of them. And we know their orbits pretty precisely already. I hope that answered the question.
Okay, we have a question from Alice. What does kinetic impact mean? Simply the kinetic motion of the asteroid?
That means we impact an asteroid with a spacecraft. Just the kinetic impact is just means we impact it. Use the momentum of the spacecraft to change the motion of the target.
We have a question from Colin. Are there any risks that an asteroid is hit by a spacecraft made by humans and that it then moves towards the Earth?
We don't have to worry about it. Think that we are doing our best trying to push an asteroid a little bit. If we basically, this is very hard for us to do. A spacecraft only has this little mass and has a speed. Well, basically the spacecraft human made are or like only a few hundred kilograms in mass, or maybe 1 ton. That's the most massive ones. They will not do much to any asteroids that we know, unless we deliberately hit something at the right time, at the right point, then we will be able to change their orbit. But otherwise, there's no risk so far that we need to worry about.
We have a question from Flora. Is it true that the greater momentum, the more the ejecta?
In general, that's true, but how much ejecta we make, that also depends on the properties of the target. For example, the porosity, basically how dense, also porosity, the density, and their internal strength, frictions, a lot of parameters. So.
Okay. Why was the binary asteroid system selected for the DART experiment? And why did you choose a binary asteroid system instead of a single asteroid?
Yeah, I think we covered this in one of my in a few slides earlier. So simply speaking, this is just because binary asteroid has slower orbital speed, and if we push it a little bit, it's gonna make a big change to its orbital period, which is easier for us to measure. On the other hand, for an asteroid orbiting the sun, we push it, we change its orbital speed by this same amount. It's only gonna change the orbital period by very tiny amount, few seconds, which is really hard, impossible to measure.
What is the largest size of celestial object that can be pushed away by the current available technology?
Well, theoretically, we can push any size of the object, right? It's just a matter of how much we can push. And so larger ones, we'll push it tiny bit. Small ones, it's easier. They are easier to push, but theoretically, we can move any of them. And in terms of planetary defense, you can see here the the more leading time we have, the smaller push we need in order for the asteroid to avoid Earth, because this kind of small offset will accumulate with time.
We have a question about the images that were taken. Why did a partial image form before the spacecraft hit the asteroid? Is it because it takes time for a camera to finish capturing one image?
It takes time for the spacecraft to transmit a whole image back. So before that whole image was transmitted, before the whole image was radioed back to Earth, the spacecraft had ended its life by hitting the asteroid. So that's why we have a partial frame in the end.
I have a question. Sorry, I have a question. So are we able to predict when and where the orbiter objectors near Earth may hit the Earth, like precisely, or just an approximate position?
Yeah, if we know the orbit of an asteroid precise enough, then we can make predictions when and where the asteroid will hit the Earth. But the thing is that all the measurements have uncertainties, right? So the predictions will always have uncertainties. And so in that sense, it takes time for us to refine our determination of the orbit and to make the predictions more precise. That's one aspect from measurements. And also there are other aspects, which is that there are many small, very weak there are many weak process, like one thing is, for example, the so-called Yarkovsky effect, which is a thermal effect that can push the orbit of an asteroid very slightly. And those are very small push, but accumulating with time, that can make big change in the orbit. So we are still trying to understand all these small subtleties that affect the orbit of asteroids. And so, I should say we can make predictions, but everything has uncertainty there. And everything we do is to shrink the uncertainty.
Thank you.
All right. How much did it cost to move the Hubble Space Telescopes and the James Webb Space Telescopes to observe the DART experiment?
Oh, it doesn't cost. Hubble is in near Earth orbit. Hubble is in our orbit that's about 560 kilometers above the ground. And it's just orbiting there. And what we do is to turn the telescope to point to the target. And same for JWST. JWST is in Lagrange point. It's actually behind. It's at about 1 million kilometers from the Earth on the side away from the sun. And it stayed there. So we just turn the telescope to point to the target.
We have a question from Colin. Are there any evaluations for the risks of ejecta hitting and damaging our satellites, such as the Starlink satellites made by Elon Musk?
At the impact, I assume you're talking about the Dimorphos ejecta. And at the time of impact, Dimorphos was at 11 million kilometers or 7 million miles from Earth. So that's really, really far away from the Earth. And also, the orbit of Didymos is outside of the Earth. And as you know that solar radiation pressure will push everything out. So basically, we expect all the ejecta dust to be away from the Earth rather than moving towards the Earth. So basically, I don't think there's any risk.
How far did the DART go?
How far? If you are talking about the distance it traveled, then before it hits Dimorphos, it traveled about more than 3/4 around the Earth. I mean, around the sun, along the orbit of the Earth. So if I tell you the radius of Earth's orbit, then maybe you can do the math. The radius of Earth's orbit is 1 astronomical unit, which is 1.5 times 10 to 8 kilometers. So now it's a math problem for you.
Did the DART actually redirect the asteroid?
Well, I'm sorry, what's that? Did DART redirect?
Yeah.
Okay. Redirect the asteroid around the sun, I guess. That's what you're asking. We should say yes, but that's a very, very tiny amount. It's right now the team is discussing the way to measure that small offset, and it's very hard.
All right, we have a question from Kelly. For something so far away, how accurate is AI?
How accurate is AI? You're talking about what? I mean, using AI to navigate the spacecraft or something? I'm sorry, I didn't. I'm not sure what question is asking about.
Yeah. To navigate the spacecraft.
Navigate. Okay. Well, the navigation right now, it does not use AI technology. The DART spacecraft used the navigation technology called Smart Nav. So basically, I don't think I have a slide here. It just take image of the target and then determine where the target is in space and then adjust the trajectory. So, as you can see, the navigation has been very accurate. We hit the point that we hit is within 25 meters of the center of the figure, center of the object. So which was the target programmed previously, pre-programmed for the spacecraft. So it's already been very accurate, and I believe with AI, it should be better.
All right, that is all for our Q&A. Thank you so much, Dr. Li, for your wonderful presentation and thoughtful answers. To our audience, keep an eye out for our newsletter, and again, the recording of this event will be available online soon. Thank you all for attending.
Thank you.